Okay, so good morning, everyone. So today, we're happy to have Dr. Ioannis Rekleitis from the mechanical engineering department. So Dr. Ioannis come from the South Carolina. He has been the assistant professor, associate professor, and full professor there. And also his research is focused on the robotics and in the area of autonomous field robotic system, developing the multi-robot cooperative localization, matching, exploration, and the coverage algorithms for the marine environment. So even Dr. Ioannis from the mechanical engineering department, but his background actually from the computer science. That's also his talk. You will see that it's also very familiar with this, very close for our computer science research. So like the computer vision, learning, and the sensor network. So let's welcome Dr. Ioannis to give us the talk.
Thank you for the invitation. It's a pleasure being here. I'm new to Delaware. I just started here in January 1st. So can everybody hear me? Can you hear me all the way in the back? Okay, good. And I presume the Zoom people, if there is anybody, can hear me also? I suspect so because we're hearing echo before, so that would do it. So how many of you have watched or read I, Robot by Isaac Asimov? Show of hands. Wow, it's a smaller number of people than I was expecting. So I guess different generations, you know, like in my time, The Foundations and I, Robot by Isaac Asimov was the standard reading for people interested in technology. And many years ago, around 2000, I was meeting with a friend and for a coffee, and they asked me, "How are you doing?" I said, "Not so good." Says, well, what happened? I said, "My robot is misbehaving today." And she started laughing. And I said, "Why you laugh?" And they say, "Because you are one of the very few people on Earth that can say my robot is misbehaving today and mean it literally." And that was during my PhD. That hit me as a, you know what? It's a very cool thing to work on something that is so weird, so cutting edge, so rare. It's fun, and given that I grew up reading robot stories, it was also quite cool. Then around 2004, I got involved with marine robots, and growing up in Greece, I love the sea, I love the ocean, I love seeing what is under the surface. As one of my favorite quotes says, that if you go to the ocean and stay above the surface, is like going to the circus and standing outside the tent, meaning you don't see much. So that's from 2004. That's about 20 years plus now. We started working in the underwater robotics, and this has been my focus since then. This is me in Greece, in a shipwreck in Greece, collecting data. Second. Why this thing doesn't? No, not annotate. So in South Carolina, and here I name my lab Autonomous Field Robotics Lab, because it encompasses the main items. So the number one term is autonomy. I'm interested on robots that are going out there and autonomously operate in the environment. There is a huge field called HRI, human-robot interactions. It's great. I want to minimize it for my robots. It's very important for other robots, but for my robots, I want the robot to be able to handle autonomously what is happening out there. The second one, of course, is field. I believe on fielding my robots, on testing the robots in the field, in the water, in air, on the air, to test how they behave. And here is an example. Here is me collecting data in a cave in Mexico, 2 robots deployed over the coral reef in Barbados. Should be using the. Here is an aqua robot collecting data over a shipwreck in the South Carolina, landing and taking off of a drone from water, a robot inside the cave in Florida, and another aerial drone, an aerial robot following and landing and taking off from a boat in the lake of South Carolina. So over the years, that makes me obviously appear very old. I have worked on many projects. Obviously, we can establish a weekly seminar for me to go through all of them, but I don't think so. I'm going to concentrate to give a sparkling of the green ones, just some ideas, and we'll talk about that. So the overarching research theme, as I said, is enabling autonomy in marine robotics. And what does that entail? There is, the very first thing is you cannot autonomously move to other place, from one place to the other. You cannot achieve your tasks if you do not know where you are. So estimating the pose of the robot in the presence of uncertainty is a fundamental problem, and I'm gonna talk about that extensively in the next slides. The second one is creating a representation of the environment. And that is important in order to know what you are seeing and where you want to go next, what you want to see next, all these kind of problems. And what kind of representation you're going to use depends on the type of robot you have and the tasks you want to achieve. Finally, we want to be able to plan a safe path between different locations. You do not want to go and there are different criteria that we're going to be employing. One of them is you do not want to go from here to Smith Hall via Philadelphia. It's a perfectly good path, but maybe it's a little bit too long. You do not want to bump into things, and you want to be seeing things. So maybe there is the shortest path takes you through an area that doesn't have many features. Maybe you want to go see something. And as part of the more general problem, planning. Where do you want to go next? There is one area that I'm not covering, and I'm looking forward to collaborate with several of my colleagues in mechanical engineering, and that is how do you control a robot to follow a trajectory? This is the control problem. We have done preliminary basic things using a PID controller, a very basic controller, but I'm looking forward to expand this to more interesting areas. Again, robots deployed in different environments, coral reefs, shipwrecks, caves, and surface vehicles. So the applications areas that I have worked so far, and that in a way, you can think of them as aligning also with grants that I have received, is monitoring harmful cyanobacterial blooms. Most common name is algae blooms. Algae blooms are in salt water. We were working in fresh water, and there is mainly cyanobacterial in these cases. Exploring and mapping underwater structures. We are focusing on shipwrecks, but the same techniques apply on oil rigs, on offshore energy things, or things like that. Exploring and mapping underwater caves. I'm fully certified cave diver. I find that as a very fascinating area to be. And it is also very interesting research-wise, because when you are in the cave, you are having a full 3D structure. There are no, you can go up, you can go to the side, you can go anywhere in 3 dimensions, and it's much more interesting. This is equivalent to driving drones indoors. So let's say you're flying a drone in here, and you want to ensure to go maybe along this corridor, but also you can fly over the seats, but you don't want to hit the people sitting there or things like that. You cannot go straight up. You're gonna hit the ceiling. So it's a very complex place. And monitoring coral reefs, as coral reefs are very important for the biodiversity of the ocean, for sequestering carbon dioxide. They're very, very important areas. And finally, mapping archaeological sites. Growing up in Greece, you cannot dig a hole without stumbling into some ancient artifact. It's, like it was everywhere around you. You go downtown Athens, the city that I grew up in, you always see Acropolis there, and it's always there. I was exploring that picture is from a project that I was collaborating with a marine with a marine archaeologist. This area, these big things here, these things here are huge marble columns that they were harvesting. They were taking marble out of the mountain, bringing it back down to the sea and loading into boats. So this was an ancient dock where they have collected, they were putting them, and every so often an accident happens and one of these 5-meter long marble columns fall into the water and stayed there for 2,000 years. As I was collecting data around, I found a little piece of pottery. So I showed it to the archaeologist, and she said, "Oh yeah, this is from late Roman period." And I'm like, "Oh, cool. How do you know?" She says, "First of all, that's my job. Second, you're looking at the lips and a little bit of how the handles are attached to it. It's very easy to identify." And then she goes, bloom, and throws it back into the water. And I'm like, "What?" She said, "Yeah, that's everywhere. Don't worry about it." So, marine archaeology. Let me give you a bit of a sense of what's going on. We have 3 different types of environments when we're dealing with marine underwater environments. The first one, the obvious one, is mostly flat. And the vast majority of marine robotics is dealing with that environment, the top one. You are flying over something. So imagine if you are having a drone outside and you fly over the buildings. You go 400 feet high, like 100 meters high, 200 meters high, and you fly over and you take data looking downwards, and then you do whatever processing you want to do. More interesting is when you have structures. So for example, you fly near a bridge, or in our case, around a shipwreck, or around the oil rig or something like that. And then, of course, the ultimate goal inside the underwater environment. So mostly flat. The problems that you have to ensure is that you somehow look a little bit in front of you, but mainly downwards. You do not want, if there is an obstacle popping up, and to bump into things. But in general, you are flying over it. And this is, like an aqua robot, little bit of an inside. Putting the sonar on top of it made it a little bit too heavy. So the robot is struggling to keep up. That's why it's swimming very funnily, and it constantly sinking. The way I have solved the problem is I found an area that had the slope. I set it up at the top of the slope, and as it was sinking slower, it was catching up. Swimming around a structure, you have to ensure that you don't bump into things. And also, things are not below you. Things are also on the side. How do you map these things? This opens up interesting problems. And finally, operating inside the cave, letting a robot move forward without bumping into things. This was preset to run forward for 30 seconds and then stop. So we found an area in this that we had enough clearance, no active obstacle avoidance. Lots of work to be done still. So two main areas to work on, open water and overhead environments. If you operating in overhead environments, you need to be able to, you need to be certified. There's a sign there with death saying, stop, go no farther. A robot went farther because, hey, it was not afraid, and cool deployments. As I said, best viewing angles, when you're in a flat terrain, you want to look downwards. You want to see as much of the bottom part. If you are looking at structures, you do not want to look only downwards. You want to be looking also a little bit forward, but not too much up. Most of the time, the bottom half of your screen is going to be blue water. So you are wasting image real estate for that. And then, of course, overhead, you want to be able to see both the ceiling and the floor and the sides. So centering around is important. So the main area that the main approach that we use for localization and mapping is visual inertial. So one question is, why visual inertial SLAM? Well, first of all, most important, there is no GPS underwater. Electromagnetic signals stop at the surface of the water. And yes, if you want, technically, there is some possibility to do this and that and the other. There is no GPS underwater. So you do not have the ability to localize the same way you're doing it with your phone, and you can find your way around town. The vision is cheap. It's lightweight. We're using it all the time. It's power efficient. We do not emit energy in the environment. So it's interesting. And most important, the visual cues provide semantic information. If you see something, you can identify what it is most of the time. You can say, this is a coral, this is a fish, this is a piece of Roman pottery, this is a piece of marble, this is a shipwreck, this is something you can identify. If you get other sensors, you are just getting, oh, there is something there. What it is, no idea. And the inertial measurement unit provides scale. Now, how many of you have used an IMU? Actually, all of you have used an IMU. Every time you use your phone and you switch the different orientations and your screen changes orientation, it's because there is an IMU inside the phone that measures the gravity and tells you that the gravity points down that way or points down this way. So that's how you do it. So everybody have used an IMU. IMU provides inertial measurement unit, provides measurements of linear accelerations and angular velocities in absolute terms. And because of that, we can extract the scale information. So the marine domain is quite challenging. First of all, you have outside forces. You have currents, swells, surge, waves, and wind. So a robot never is by itself. There is always some forces applied into it. And for example, in a lot of caves, there is flow that is pushing you into the cave or out of the cave, and that can be quite significant. It's an unknown environment, and by unknown environment, I mean it's a completely different, it's an alien place. It's different from all the stuff that you are used to seeing every day. So it's a cool environment, but it's different. So you have to be aware that you're gonna encounter things that are kind of not used. And also it's a dynamic environment. Things are changing all the time. There are fishes swimming around, sponges, seaweeds. There is growth and deterioration, like something that was there last year, you go this year and it has disappeared. Corals are dying massively the last several years. Coral bleaching, where there was a colorful coral, now it's a stark white coral. All these are problems that we have to deal with. Now, in perception in particular, did I mention there is no GPS? For vision, forget all this beautiful vision that you have above water. This nice crisp images that all the data sets that machine learning people love to play with, ImagineX and all that kind of stuff, forget it, they're not there. This is the kind of images that you are seeing. There is low visibility, there is light and color attenuation. The deeper you go, the sunlight disappears and the colors disappear. First you start with red, then green, finally blue disappears. There is low lighting or sometimes no light at all. If you're diving in the night or if you are operating inside the cave, there is no natural light. You're carrying your own light. There is scattering, the visibility, even in the best case scenarios, you cannot see very far. So you have to concentrate on what you are seeing around you. There are many different ways. So sonar that I'm showing up there, it gives you a bunch of points. You have no idea what it is. Vision, you can have an input image RGB, you can label the image, and you can provide a visualization. So you can say, this is a diver, this is a rock, this is an object. Because of all these challenges with underwater vision, we did a comparison with a couple of comparisons of open source visual odometry and visual inertial odometry packages, and they didn't do very well. We ran them on a variety of data sets and it was not looking very good. I'm not gonna go into the details, but you know, as you can see, the ones that succeeded, the data was not consistent. There are several meters of error over time. So there is a failure analysis here. I'm thinking I'm running a little bit late, so I'm gonna go forward into the more meatier parts. So we worked on a package called Svin2, because that we added some extra stuff, where we're fusing sonar, visual, inertial, water depth, and magnetometer data for accurate localization. We added loop closure, so when the system comes back into an area that we haven't seen before, that we have seen before, we can close the loop and say, oh, these two things looks very similar together, so they are taken from similar locations. And we removing the outliers. This is the functional diagram of how things are working, gives you a good overview. We start with from a previous publication by a whole bunch of great people from ETH Zurich. It's called OCVIS. So the green parts are OCVIS. So they're the pipeline using IMU and camera comes from OCVIS, and we augment it by introducing the depth sensor. The depth sensor gives you absolute information about the z-axis, how deep you are. Depth, when I say depth, I'm talking about water depth, not RGBD, not Kinect type of data. We're also using a sonar that scans the environment and magnetometer data. So the state vector contains the position of the robot, of the system, the orientation of the system Q formed as a quaternion, the velocities, and also the biases for the IMU. We have to model the biases because the IMU provides this great information, absolute information, but it is also drifts a lot. And the state error is, of course, the error in all these directions. And we implement by using a cost function that contains the following terms. We have the reprojection error that tells us how far pixels are, how far pixels project in the new image to the old image. We have the error from the inertial measurement unit. We have error from the sonar unit, depth error, and the magnetometer error. So the reprojection error is the difference between a key point measurement in camera coordinates and the corresponding landmark projection according to the projection model. So we saw a key point, how does it project back, and how that compares to where that point was supposed to be from our model as we're moving forward from our map. We pre-integrate and we measure both the robot pose and speed and the bias error. The sonar range error, it's an interesting one. We have a pencil beam scanning sonar. So it's the little red tube that can be seen here that is scanning into a plane in front of you like this. It's a mechanical beam, so it's just scanning around, but it's called pencil beam because it is very narrow focus. So you're getting just a point. You do not get a beam that is spread out and anything can reflect back. It's just one point. Now, the problem is, at this moment that I'm looking at, let's say, at you guys, the sonar is scanning the ceiling above me and the floor below me and the walls. It's scanning in areas that I do not see. So what we have to do is use past data that we have seen. If I was farther back out and I have seen the floor and the ceiling where now I am, and I scan and measure all these points that we have seen from vision, and then provide an error based on how far the sonar point from those cluster of points was. The depth error gives us absolute information along the gravity direction. We know how far we are along on the z-axis. And the magnetometer error provides data about absolute orientation. Now, the magnetometers are extremely noisy sensor, so you have to calibrate them based on soft iron and hard iron corrections. Some of them are the errors that you are having based on the environment that you are, and sometimes some of the errors are coming from the configuration you are at the time, meaning the metal components and the electronics that are next to your compass at the time. One interesting thing, if you are playing with magnetometer data, to point out is that you need to, if you have a cell phone and you're trying to use the compass on the cell phone, they say calibrate your compass. So you have to go around and move your robot or your compass in all directions. If you have data that did not happen, but you have moved the system in a lot of directions, you can find these parameters by doing a partial calibration, by taking all the data that you have done over the time in your deployment and map it. So there's a refinement at the initialization because we want to start where we are using measurements from the depth sensor and also depth measurements like 3D structure from the stereo cameras in order to initialize the IMU setup with the parameters, the biases, and then we move forward. Finally, as I said earlier, we have introduced loop closure. This was very, very important because when you are doing a lot of long deployments, you go far out, any system will drift. And when you come back, you have to correct that drift. We're using a standard technique called bag of words. So we take every image and we are extracting what are the dominant features, and we are encoding them in a bag of word formulation. Then when we get a new picture, we look at the database and we find out, is there something that looked like that in the past? So we are then extract from these common fits, from these two common images, the relative position. Here's an example. Without loop closure, we have like more than 10 meters of distance at the end. So we started at 0, 0, 0, because we have no idea when the camera starts, it started 0, 0, 0. We started going around, we turn back, sorry, I keep forgetting, you coming around this area, and we start going back. And as you can see, we drift. Now, a human can easily say, well, that's easy to match, but trying to match them is not so easy. So when we look back, we're getting, if we're seeing the same place twice, we're doing the loop closure. Here is some results. This is from a sunken bass in North Carolina. It's been put there as an attraction for divers, so we went around and mapped it. As you can see, the sun was low in the horizon, so we just came up and we're seeing towards the west direction here. The visibility is horrid. So being able to map these things, it was quite challenging. And here is where we're gonna go around, and we're gonna have drifted, but when we see the same area, the steps, it locked together. Then we go back and we swim through the bass, because why not? It was open, so then we're gonna drift again. Here is mapping a cave inside. It's a Devil's Eye cave system in Florida. Swimming through, I think we're going to be accelerating. Yeah, so I'm not swimming that fast, it's just the data coming along. And you can track our position. This was a narrow pass, so we're going through a narrow area here, going around, and swimming. This is the Spain in Cueva del Agua. That cave has been mapped manually by humans. There is a human survey in 2019. When we did the visual inertial in that part, as you can see, you can match the scale completely. So we actually had a good results. This is from SVIN, from visual inertial. The data that are coming out are, it's a sparse representation. So here's a wreck. Here is mapping the wreck with the two GoPro cameras. And here is, we did 3 deployments. Actually, the two of my students that are in the audience, we are working right now for tomorrow night is the deadline for the next publication. This is data from that paper. This is me mapping that part of the shipwreck. And this is the 3 different data sets that have been extracted. I said earlier that shipwrecks are structured, so you are only seeing, it's not an overhead environment. This shipwreck has areas that you can see in here and inside here, and we have gone inside and map. I have gone inside and mapped that area there. You can go into denser representations. Here is a image. This is a view from one of the caves. We are running Colmap that can run many hours to several days. It's a global optimization package. It maps data from different views and collects all the data together. We had a paper with my colleagues from Stevens and Dartmouth College where we mapped the same thing but frame rate. So using the stereo data, we can do dense stereo that is almost the same as the bundle adjustment. I keep talking about how great is vision for semantic segmentation. Here is more recent work where we're looking at the cave scenes, what we are seeing inside the cave, and we can extract semantic information. So for example, when there is a black area here, everybody can see that this is most likely an opening to unexplored area. So we can, a deep learning system marks that area as open areas. Very important, every time one of the cardinal rules, if not the number one cardinal rule, well, maybe not, one of the top cardinal rules in cave diving is you always have a continuous line that takes you to open water. So when you finish that line, you just pop to the surface and you can breathe. Continuous line. This is what we call a cave line. So here is the cave line. Here is the cave line. Here is the cave line. Here's the cave line. This is very important. So we want to track the cave line because that gives us a one-dimensional guideline through the cave. So we map the cave line. We looking at obstacles that are the first layer and also obstacles that are farther in order to do our path planning. Again, open area here, ground plane, cave line, first layer. We want to be able to identify arrows. These are markers that go on top of the cave line that tell you which way is the exit so the robot can help them to navigate. And also, very important, identify scuba divers. You want, when you are operating a robot, to give always the right of passage to scuba divers because they could have an emergency, they could be needing to get out of the cave fast. You don't want to stop there because you are mapping the cave and block the people. And so being able to identify people. Here you can see it in video form where we are predicting the different components. Also identifying the area where the cave line is attached to rocks because that usually signify a change in the direction of the cave line. And of course, as I said, divers. Another semantic information is mapping of corals, where, as you can see, we have used we have collected data in the coral reefs of Barbados. All the Caribbean has the same families of coral, so that we can use that. And here is the coral reefs and where we identify the different types of corals. And the advantage combining this semantic information with a denser visual inertial state estimation, we can identify where the corals are and also identify point clouds that are represent different types of corals and measure the size of the corals and also count and say, okay, in that transect we find that many brain corals, that brain finger corals, that many star corals, and so on and so forth. Vision always fails. Vision is gonna fail. And the most common failure in underwater is we swim happily looking at a scene, a wreck, a coral reef, something. And as we approaching, let's say in this case, the end of the shipwreck, the area that we're seeing features goes lower and lower and lower until in the end we just see blue water, in which case the vision has failed. We proposed a switching estimator, switching between a model-based estimator and a VIO system. So we have a health monitoring, VIO health monitoring. So we're seeing how many features are we seeing? Are they features consistent? Is the visual inertia tracking properly? And when it stops tracking, we switching to the basic estimator that is using the IMU, the depth sensor, and the motion commands, a model-based estimator that tells us how the robot moves. So in a cartoon form, we track both trajectories, both the primitive estimator and the VIO. And as we're moving forward, the health is okay. So we're using the vision, the VIO-based estimator, which is the more accurate one. But when the health didn't work, we switch and we use the primitive estimator, then switch back to the vision-based estimator, and so on and so forth. Now, the important thing is we initialize every time we switch to the last pose that we were there. So we have a continuous estimate of where the robot is. Certain parts of it are not as accurate, but the other parts are, and then we can put it together into the global optimization process. We're looking how many key points are tracked, how many features per quadrant, the ratio of new to tracked key points, and average corner response of the detector, and so on. And so on and so forth. So here's the results in two different environments. And while most of the non-switching parameters failed after a while, some of them recovered, some of them didn't. We got the lowest results just with the switching estimator. How am I doing in terms of time? 10 minutes? Okay. So, as I said, we want to be able to localize, find out where we are. We talk about SVIN and different techniques we use for that. We want to find representations of the environment, and that can be a sparse representation that SVIN gives us. It can be a dense representation or semantic representation, as we saw with the cave segmentation work. The next one is how to go between different places. So we took a classical optimization framework called TraJOP, trajectory optimization, by Peter Abil and Ken Kohlberg and a lot of other people that work on it. And we adjusted to work for underwater robots. And we starting with a basic trajectory, and we ensure that whenever we have objects, we go away from it, but however, optimizing the trajectory, trying to find the shortest path. As you can see here, the optimization takes into account also the different poses. The robot can switch its orientation in order to go around the obstacles. Now, we have encoded a fair amount of space around the robot in order to ensure that we do not bump into things. And here is a deployment of in Barbados, where the robot avoided corals and swam around and was affected a little bit by swerve. So that's why you're seeing a little bit of a rolling around. Unfortunately, that happened unfortunately, this was in January 2020, and in March, we were not able to go deploy the robot anymore for a while, so this is future work. We extended this work with what we call Aquavis, and the idea is to look at visual objectives and bias the trajectory optimization that we saw in the previous slides to take into account the visibility of these objectives. So the objectives can be corals. If I'm seeing corals ahead of me, I want to go see towards that coral. If I'm seeing corals on one side and sand on the other side, maybe I want to go towards the corals. Or it could be another robot. Maybe I want to be following another robot. I'm tracking another robot. So we are projecting in our future position where we're gonna be seeing the features that we are interested in and bias it towards that direction. So as you can see, Aquanav goes on a straight line here, while Aquavis is trying to keep these landmarks here. Over here, it's a simulator over a shipwreck. We do not see almost nothing as we're moving forward. This one goes down and tracks along the trajectory to track the shipwreck and keep most of the shipwreck in view. So we can have two robots. One robot goes close to the shipwreck, the other robot goes above it and track and map the shipwreck. Another approach we explored, it was using a deep learning framework where we collected data on a simulator and from a real shipwreck. This is my student Nares, is currently at Hui, and as we collected the data, we looked and we said where the camera went next, and we used that as a training. So we were able to extract this data and train a network. If I'm seeing this, where is most likely to go next? And the good news is that it worked. The bad news that it worked, it was quite specialized. So the simulated data worked well on the simulator. The real data worked well on the real data. This was work we did around 2019, 2020. So I'm pretty sure with the newer deep learning techniques, we can expand it and move it forward. So here is my student Nare collecting the data. And these deployments gave us some interesting insights. First of all, what is the difference between exploration and coverage? This raised the question, what's the difference between exploration and coverage? In exploration, we go towards the frontier, the areas between known and unknown spaces. The problem is, in 2D, it's very easy. It's very basic. The environment is bound. If I don't see what is happening behind there, I'll go around it and see what is behind there. When you have a 3D structure, it is the unknown can take you to blue water. Like, imagine you are trying to film a house from the outside, from a drone, and you're like, oh, I haven't seen there. You go there, you see the sky. Oh, look, there is a lot more space. Let me go explore. And you go off to La La Land. Also, I can tell you that even people, even humans, that we have a basic understanding of things, we cover a structure, we still miss a lot of things. So coverage, on the other side, we go on a predetermined pattern and cover around. We move a sensor over all available observable space. It works well in 2D and 3D. The exploration, we want to find, as I said, the boundary between known and unknown space, which is called the frontier. Where to sense next, when to ignore an unexplored space. One solution, if the area is too small for the robot to enter, that's blocked. Or if it is blue water. And when we exploring is what's the difference between free space versus structure. I think I'm almost out of time. We did a new algorithm for surface vehicles for coverage. Nobody have done that before. Everybody here have heard of skeleton, medial axis, Voronoi diagrams, hopefully. It's the space that is equidistant. It's a one-dimensional retract. It's a space that is equidistant from obstacles, the skeleton of a shape. By looking at the distance between the skeleton and the boundaries, you can construct closed loops for going around and sampling. Where to go next? If you were seeing this thing, where would you want to go next to explore? Would you go around that thing, that thing? Interesting questions. My current students, Hyunkil and Michalis, which are here, Ibrahim, which is still in South Carolina, several people in the past have worked in these projects, and acknowledging collaborators and people. Thank you.